Hi, my name is Paul Montgomery. I'm a CNRS researcher working at the ICube laboratory in Strasbourg, France. With Audrey Leong-Hoi, a second-year PhD student, we've written this review entitled Emerging Optical Nanoscopy Techniques in order to address some of the new imaging techniques which are capable of subcellular resolution or detection over wide fields. Far-field optical nanoscopy presents many new solutions, which we can see here in a plot of the history of the different techniques in terms of the limits imposed by diffraction and then nanodetection. This enables us to see the many super-resolution techniques that provide improved resolving power, indicated in red, and the nanodetection techniques that allow the characterization of unresolved nanostructures, indicated in green. Another way of apprehending the many techniques is in the form of a classification scheme, first distinguishing between near-field and far-field, the latter being the main interest of this review. Then we can make an important distinction between super-resolution techniques and nanodetection techniques, which can then be classified into those that use contrast, phase measurement, deconvolution, and the use of nanomarkers. We illustrate super-resolution techniques with tomographic diffractive microscopy, in which by varying the illumination angle to increase the synthetic aperture size can attain a resolution of 97 nanometers. This has been achieved for unlabeled transparent specimens. Here we can see the remarkable details of a diatom, with a system that has been developed at the MIPS laboratory in Mulhouse, France. Our own work at ICube concentrates on using the phase of the light in order to access information on nanometric structures. Coherent scanning interferometry has been used here to produce high-resolution measurements of layers of synthetic hydroxyapatite in A and B, the buried details of the nucleus of an onion cell in C, and buried defects in a 3-micron thick polymer layer in D. One way of increasing the contrast is to reduce the background signal using an anti-reflection coated substrate in a cross-polarized light system in the SEEK technique. In the video on the left, we can clearly see the nanometer-thick slime trails of bacteria that are moving, and this without labeling. Finally, on the right, in dual-objective 3D storm, by using nanomarkers consisting of blinking fluorescent molecules, superlocalization techniques can be used to build up a higher resolution image, in this case the very fine actin cytoskeleton in a COS7 cell. In conclusion, we present here some of the major emerging nanoscopy techniques that are becoming important for imaging in biophysics and medical applications. We have presented a useful classification scheme for these many techniques. To finish, some of the main challenges that now exist are for deep tissue imaging, applying correlative and energy operator techniques for signal processing, to use adaptive optics to move towards what we could call intelligent nanoscopy, and then miniaturizing the probe heads with microsystem technology and optical fiber-based systems.